In the next two webcasts, I want to break down what must look like an overwhelming or intimidating amount of chemistry. I want to break it down into individual steps, and I want you to really be able to examine that individual step as a certain type of organic transformation that you're familiar with. It might be some functional group manipulation. For example, taking an alcohol to a phosphate ester, so phosphorylation. It might be an elimination step, or it might be a new carbon-carbon bond forming step, like an aldol reaction. I want you to see that each of these steps at their core really are just organic reactions that you've already learned about. I think it would be helpful as we go along, if you pause the recorder, write down this chemistry for yourself. The act of writing down and following each of the individual carbon atoms will be very informative for you. Pay attention to the stereochemistry, pay attention to what new bonds are formed, what functional group transformations take place. Worry less about details such as names that I might mention, etc. Those are not things that I think are so important for you. So the way I want you to understand this first step, which involves the two building blocks, the erythrose 4-phosphate on the left and the phosphoenol pyruvate, is to think about phosphoenol pyruvate as a masked form of an enolate anion. So for example, if we had a nucleophile, which could be the active site side chain that would, say, attack phosphorus in this phosphate ester, and you don't know yet the details of how bioorganic phosphorus chemistry takes place. We're actually going to study that in an upcoming webcast, but for right now, just imagine that there's a nucleophile that attacks phosphorus and releases an enolate equivalent. So that structure that I'm drawing is one that you should now be familiar with as an enolate anion, which is used, for example, in aldol reactions. That's where you've encountered it before. And so indeed, you might very much imagine that what's going to go on in that next step is this enolate-like equivalent anion is going to add into the aldehyde the carbon-oxygen double bond of the erythrose 4-phosphate. So at carbon atom 1, we expect to be then making a new bond between carbon atom 5 of phosphoenol pyruvate. We expect the phosphate group to go away. We expect a new carbon-oxygen double bond, so you can see that from the curved arrows that are drawn down here. The carbon-oxygen double bond will be formed at position number 6, and a new bond between carbon 5 and carbon 1 in what looks an awful lot like an aldol step. And indeed, that's exactly the way I would describe that. Epsp Synthase is an enzyme that effectively carries out the aldol addition step. We expect then at carbon atom number 1 a new hydroxy group that you could have imagined by coming about with the stereochemistry shown. A certain face of the aldehyde would add. Those aldehyde faces are diastereotopic, and so by that way, in that selective facial addition, we can produce the stereochemistry shown. This molecule, you don't need to know the name of it, but I'll just tell you it's deoxy, and the reason is deoxy is there's no hydroxyl group at position 5. It's a sugar, arabinose, so deoxyarabino heptoleuconic acid. That's monophosphate. That's the name DAHP. The next step is we're going to do a cyclisation, and this is how the carbocyclic ring is formed. The molecule that's formed is dihydroquinate, and dihydroquinate synthase is a complex enzyme that does a bunch of chemistry, and I really want you to go through it right now and try and it's complicated, but I think you can break it down and understand everything that goes on in the essentially 3 steps or so that take place in transforming this linear or open chain molecule into this carbocyclic system. This carbocyclic system has 6 carbon atoms in the ring. Those 6 carbon atoms eventually become the 6-membered ring of the benzene in phenylalanine or in tyrosine. So the first thing that happens, at least in a formal sense, is an oxidation at carbon atom number 3. And now if we oxidize the carbon atom number 3, and so what I mean by that is that what used to have a carbon hydrogen and an oxygen carbon-oxygen single bond has now transformed into a carbon-oxygen double bond with no longer having this hydrogen present. that oxidation, if you just imagine now a carbonyl at position 3, would allow us to deprotonate one of the hydrogens on the alpha position to that carbonyl, and that would allow us to make a nucleophile there, and that nucleophile could do an aldol type reaction into carbon atom number 6. So we expect a new bond between 4 and 6, and we expect that the carbonyl group at position 6 has been replaced with a carbon-oxygen single bond, a hydroxyl group. And that's exactly what happens. And again, there's a specific face of this carbon-oxygen double bond that reacts to make the structure that's shown here, dihydroquinate. Next, the enzyme dihydroquinate dehydratase removes the elements of water that come from one hydrogen on position 4 and the OH group on position 6. So we eliminate water across the 4-6 carbon bond to make a carbon-carbon double bond. And the next thing that happens is a hydride reduction. Hydride comes from NADPH. That's a cofactor, a coenzyme. That coenzyme provides H- hydride, and essentially this hydride reduction is a nucleophile addition to this carbonyl group. And that produces the molecule shikimate, which has the structure, or shikimate, because it's a carboxylate, shown here. You can imagine again that there's a particular delivery of the hydride to one face of this carbonyl. It looks like it comes in from the top, and we produce this stereochemistry that's shown. So H comes in from above. The next thing that happens is phosphorylation of that hydroxyl group by a kinase enzyme. So remember, phosphorylation is a way to make a good leaving group, and eventually we'll use that as a good leaving group, but not yet. The next thing that happens is the Epsp Synthase. Epsp Synthase stands for enyl pyruvate shikimate phosphate. So this is shikimate phosphate, and enyl pyruvate means we see the second molecule of phosphoenyl pyruvate getting involved. Actually, the way that this gets involved is different than the way that it was used in the first case. In the first case, we used it as a nucleophile, but here we're going to do a substitution reaction on the phosphate group, and so the substitution reaction is going to be substitution at this sp2 center by, as we'll see, an addition elimination process, and we're going to substitute the phosphate group with the hydroxyl group here, and that makes the enyl pyruvate shikimate phosphate. That's the structure shown here. And so a substitution where the hydroxyl group has substituted for the phosphate group on the enyl pyruvate, phosphoenyl pyruvate molecule. So now we've used all 3 building blocks, we have all 10 carbon atoms, and that's where we're going to end this first webcast. We'll pick it up from there and show you how this intermediate goes on and forms the aromatic amino acids.